Hello, welcome to a video. Should be really good audio. Got a new microphone, does like noise filtering and whatnot, and it picks up voices really clear. Um, I've got a really small mount though, so you can't actually see it in the shot, but that's all right. Um, Sounds like it is working fine, so I will take these off to look a bit more normal. So yeah, welcome to the video. And the last video I gave a quick update about my health. So for the last like year and a half, I've basically not been able to do much work. I've had a nerve pain in my face, trigeminal neuralgia, it's what it's called, and I've now got a sweet scar on the back of my head where they like mentioned things. But let's not get into specifics on that. If people are interested, then I can kind of talk about it. But, maybe one-on-one personal type thing. So I thought I would just, now that I've got a new microphone, kind of just do a walkthrough of what my operating system is. So I've made an operating system. Well, I'm still making it. It went on a bit of a hiatus, I guess you could call, because I couldn't really think clearly to do much. But um, it can do like a bunch of stuff. It has a shell. You can like scroll up and down in it. It's got some tests, but like if we go text color, it'll like, ooh, pretty colors. For some reason I chose green is like I don't know, that's what it does. Um, it's got like a printf, which um, does like a bunch of stuff, and all those test paths. If the test failed, then it'll like just crash. But yeah, what I was doing was kind of before my um, nerve pain started was I was starting to work on like a window manager. So this should be 80 by 40. So let's do like 40 by 20. Should be a bit smaller. Um, the shell doesn't really resize with it. But what I want them to do, which maybe I've got a shortcut for it, need to be in the machine and then like maybe it's like any hotkeys. Nah, I can potentially look to see whether there's a hotkey or not. But I thought I might dive into the code. So I did a very, very, very early on video on how x86 assembly works, to my knowledge. The audio that was probably quite rubbish because I think it was my second video. So I thought I'd do a quick kind of intro on how x86 assembly works because this operating system is written in x86 assembly. Has the limitation it can only run on x86 computers, but that's fairly ubiquitous. Um, Basically, every PC is running x86 assembly, and some might use like a ARM processor, which has a slightly different instruction set. When I say slightly different, it might be heaps different. I haven't done any assembly in it, so I'm not too sure. Um, there are also like a bunch of other assembly dialects basically that target different instruction set architectures, ISAs. But here we're focusing on x86 assembly. So like a very quick like once over. Well, I'll show you what the code looks like. So like say for example where we keep it. We have to boot somehow. So let's look at boot.asm. We can kind of include stuff. this file is kind of making it lay out a bit different. I was playing out with things. So if we open up that source boot 16, uh, funny thing, even though you might have a 64-bit PCU, 64-bit CPU, not PCU, it actually starts in 16-bit to start with. That's just how it starts. And from 16-bit, you need to do like a bunch of stuff, and then that will actually go into 32-bit. So then we have like a 32, and this is the 32-bit. So this is where the main kernel is, and it does some initialization, and it has like some panics and stuff, and like it does like a bunch of stuff as well. And from there, the rest of the source is like kind of split out into different places. And if you want 64-bit, which is called long mode. So maybe I'll go into like just all the modes. So x86 modes. So you have real mode, which is the 16-bit. It's based off like the well, it started from everything's like backwards compatible. So this actually came from the 8086 from memory. I could be wrong. And then you have protected mode, which is the 32-bit, and that has some mechanisms in it so you can like have some protection, hence the name. And then you have the long mode, which is the 64-bit, and a 64-bit PCU CPU can run on any of these modes, and it will actually start in real mode, then go to protected mode, then go to long mode. And a 32-bit is the same, except it just won't have the long mode. But the thing I target is just the 32-bit one. And the reason for that is purely because I haven't bothered to. I might just pull that up there so I can see the time. I just haven't bothered to learn much about the getting into long mode and whatnot. But yeah, so I say that you start off in the real mode, and then from the real mode, you need to do a bunch of stuff that initializes some things that the 32-bit environment expects. And then once you get into the 32-bit, you shouldn't really go back into the 16-bit, and it's actually more difficult to do so. But there are some reasons why you might need to like talk to the BIOS or something like that. Um, but the idea is you want to like kind of get everything you want to start with. And so how it starts is you have I also um I only target the MBR style boot. I don't actually support the UEFI style boot just yet, which is more modern. Ironically, I got a new laptop, and that laptop does not support the legacy mode at all. So I literally can't run my operating system on it. But the one I'm talking to you on, it would work if I write the image to a USB stick or something, and then plug it in and boot off it, and it would work fine. But yeah, you basically have a hard drive, and on that hard drive you have a master boot record, and that basically looks after all your partitions. You can have four primaries, four primary partitions, and the four extended partitions. So basically, 8 partitions in total. The other way is the unit. This one is called MER. and the other one is unified extendable something. And it's just UEFI. And this has like GPT, not like Chat GPT, but GPT partition manager. Um, and that will have basically unlimited um, partitions you can have on there. I think there might be a limit, but like for all intents and purposes, it's unlimited. But as I said, I don't target that at the moment. So how it, well, we're recording macros, so get out it and start. How we do the booting process is we have a BIOS, so that's the basic input output system, BIOS. And so this basically is what the computer originally, not originally, well, kind of originally, wrong word there. It's what the computer initially boots into. Um, computer boots into BIOS. And the BIOS expects, well, the BIOS kind of does like a bunch of stuff. You may have seen the BIOS if, like, when you first boot, you like push like F2 or delete or F10, like whatever based on your computer. And when you it boots into the BIOS, and then the BIOS will scan partitions looking for a hard drive that has looking for a partition that has got a certain flag set, the boot flag, and then so it's got to have a boot find boot flag on partition, and then it will go to the then it will pass control to the boot sector of that partition. Some BIOSes allow you to choose which partition that you want to do, but originally it was like it would just pick the first partition that had these had the flag set. So the flag is, if we just open up a new window, maybe go down here, if we go into that source boot 16, if we go into here and like magic, and what do we have? DD magic. We have it in some include file, of course, here. MUR magic. Why did I do grep twice? That's why. So it will look for AA55. Where are we? We want to go there. So the as far as I know, the boot flag is actually that magic flag. So the boot flag is what did I say it was? AA55. 0xAA55. 0x is basically saying it's hexadecimal. So hexadecimal is like 1, 2, 3, 4, 5, 6, 7, 8, 9, and then instead of 10, it will go A, B, C, D, E, F, and then 10 is actually 16. So it's basically base 16. It's not that scary. You've probably learnt it in like some level of math at school. It's just called base 16. There's ways to convert it, but on a computer, it's actually quite useful to know base 16. You can also do it in like binary, but that's like a bit more long form because that will be base 2, and that's like you go 0, then you go 1, and then your 10 is actually 2 because it's base 2. But anyway, side note there. Once it finds that boot flag of 0x55, it will start at a certain place. It will start at. Do we say where we are? Of course we don't. So it's going to start at like this thing here, but how do we say that's where it is? Of course, this NBR entry. I think all of that is in like source include MB. Nah, none of those. Boot includes MBR. I don't know why I did it like that. But you may want to go up, please. Sorry, I switch between keyboard layouts. I've got a few keyboard layouts on the go just to, I don't know, mix it up a little. So then it will find the boot sector. So the boot sector is 512 bytes long, and that boot flag takes up 2 bytes. And we can tell that because there's 4 hex things. You can break down a byte into a nibble, which is just a 1 hex digit. But yeah, it basically looks for 2 bytes, which is AA and then 55, and takes up 2 bytes at N. And I did like a control A there to increment, which I didn't want to. So all this is done by the BIOS. So the BIOS is scanning partitions, and it's going to look at the last 2 bytes of the first 512 bytes of every partition, and if it has AA55, it's like, golly, that's my partition. That's going to be the one that I'm going to boot from. So then it will load up those 512 bytes. Boot sector is loaded at 0x7c in memory. So your memory is like kind of like arbitrary, but it's like as long as it needs to be, but limited by how much memory you have available on your system. And the BIOS will just kind of load up that at 7C00, and then it will basically just do a jump or go to and see. There's no real equivalent in most other languages because most people frown on GoTo, but in low-level assembly, that happens and it's called a jump. And basically, high-level languages are assembled in a way that you will have jumps. So then you basically have your code, and then your code will look like what we had here. And so that's what this org means. It means like origin, I think, from memory. So in this dialect of x86 assembly, I'm using FASM, the FASM assembler, flat assembler, it's called. I need to specifically say that it's 16-bit, so I'm here to say use 16. Other dialects like NASM and GAS and stuff have similar kind of commands. It's not really a command. Some like kind of things that will say it's 16-bit. This public boot is basically saying I'm exporting a boot because the way I assemble my entire operating system is each little chunk is put into a ELF file, which is executable loadable format. Ironically, my operating system has no support for ELF files, but on my host operating system of Linux, it does support ELF, and I basically uh, assembled it all into separate ELF files, and then I can use a linker script that will link it all together and put it in the right place, which I believe is in. No, it's not there. Uh, well, we can probably look in uh, build source, and that will tell us how. LD. Um, where do we link? Um, yeah, LD. So we do source link it. I don't know why I didn't find that source linker. Ah, I just didn't tab the extra time. So in this linker script, we're saying the entry is boot, and you may recall if we do that split, nah, not that split, that split, and then want to go over there and maybe go back to here. So we're exporting boot and we're saying our origin is at that 7C00. This is just a variable that we're setting, but it doesn't take up any instructions. And this is the same, doesn't take up any instructions. Here's another like label, doesn't take up any instructions, and here's the boot label. So this is where the operating system will start running the code. And in the linker script, we say, yeah, this is the entry. Our output format is just going to be binary. We're going to say where it is. We are not going to output to the ELF file. That's usually what happens. And here we're going to say the first section is 7C00, which is that where the boot sector is expected to be loaded. And here the .text is like executable stuff. And we're going to chuck everything that has the boot label in it at that point there. And then we're going to follow it by boot 32, but we'll get into that. So we go on the boot, and we have some limitations when we're in real mode. We only have a megabyte of memory, 1 megabyte. That's all. But we can do some like interrupts on the BIOS, and that's just how it is. So here we do like a little trick. So some BIOSes can do some weird things and load us at the wrong place, but it's not really in the wrong place. It's like at a code segment. This format is like I'll get there. And again, so this format is this first part is the code segment, then this is the address. So this would basically say at 7C0, just it's there. But to fix this, you basically do a far jump, which how you do that is you basically trick the assembler into assembling a particular type of jump instruction, because you can have a short jump, you can have a long jump, and you can have a far jump. So the far jump will, where's it go? It goes, yeah, it just goes to here. That's all it does. Um, just before the far jump, we do some like magic things, and that's basically useful for my debugging. So we know like that far jump is the same as long jump. Sorry, um, it will take up 5 bytes. DD means data double, and DW means data word, and that's potentially a good segue into what different things are. So, uh, a word is going to be, if I'm not, if I'm correct, it's 16 bits, and uh, so basically 2 bytes. So you can have uh, D, DB 1 byte, and uh, gosh, you can have a word, you can have a double, which is a double word. So that's going to be 4. And you can also have a quad, which is a quad word, which is 8. And that is just how x86 defines it. There's like a massive manual that people could get. It's also like available online, which is the Intel technical manual, which will say how everything works basically, and it will say these things. And they're useful to know because you need to know how to kind of do some stuff in it. So here if we go back to here. So we do a double word, so that's going to be 4 bytes, and then we're going to do a 2 byte debug break. And a debug break is a label, and magic is also a label, which will probably get defined somewhere else. You can define stuff further down. And then here's that flush CS. So that's where we did that far jump to. We jumped to code segment 0 and then to the label flush CS, which will basically jump to here. And this will get assembled as like the right thing. And it'll basically be 7Z 0. So if a word's 2 bytes, then we go up to B. So this will be basically 0x7C0B. But if we add more instructions here, then it'll be different. Here we do like some stuff. We need to have a stack. So we're going to set the stack to build back up here. And the stack goes downwards. So here we're basically saying the stack starts there, but it goes downwards, which is useful because if it grew forwards, then it would be overriding all our code. And here we see some different commands, I guess. So here we have a mov and a push. So a mov is moving data about, and a push is pushing onto the stack, which to start with, we need to get the stack. But we also have this thing called registers that we are kind of seeing here. So we have an AX. We actually have a BX and a CX and a DX. And we also have a stack pointer and a program counter. So these ones are a bit special. Stack pointer, program counter. We also have a, what do we have? We have a BP, which we can see down there, which is the base pointer, which is used by the stack pointer. So maybe we'll put it there. And we also have some others which, well, like some other, yeah, so we have an SI and we have a DI. That's kind of used for source things, and this is usually used for destinations. Um, is that it? 6. Yeah, I think that's it. So here are your 6 like general registers, general purpose registers. So you can put whatever you want in them, and they don't really have much meaning. You can make them have meaning, like CX people commonly put to. I'll just put my phone on silent actually, because um, that is probably not good to hear a bloop, 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 bloop. So CX, that is commonly used for a counter, and AX is commonly used for an accumulator. Um, Basically where you put stuff. Now there are like some other things, like AX is usually if you have a function that returns that will get stored. That's where it usually will be. And if you do like a divide, then DX will get used as well as AX, and you'll get the division, but you also get the remainder. There's all sorts of weird stuff that happens. Um, Now, these are all 16-bit. You can also get like AH and AL and BH and BL. And these are kind of, they combine into AX, but each of them combine into AX, but each uh, 8-bit or 1 byte. And basically it stands for high and low, and high and low. So you can imagine your 16 bits are 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Could have done that quicker in Vim, but that's all right. You can imagine that that whole thing is AX, but BX is just well, it's so this is going to be AH, and then maybe I'll do like a above one, and here we'll go, yeah, and that will be AL. So basically the high bit and high byte and the low byte, and that's basically how that goes. So they're all 16-bit. We'll see maybe in a bit that there are actually 32-bit and 64-bit equivalents. I'll just do a quick teaser. So AX is 16-bit, EAX is so that's 16, and EAX is 32, and RAX is 64. And when you get to the 64-bit code, you also have like R6, R1, R2, R3, to like R16, I think it is. So you have like a lot more general purpose registers. Only 64-bit. And these are also the same, 16-bit, and you can have EDP and RDP. So like it's the same thing as above here. So the 32-bit, 64-bit, there's the 32-bit, 64-bit. And I think you can't get to the high and lows of these. There's also a couple of other special ones, but we'll come to that, I guess. Anyway, so what this is doing is it's moving 0, so it moves the right, basically the right hand. This is Intel syntax. You can also have like, oh no, this is AT&T syntax. I'll probably get corrected. You can also have stuff like move uh, percent, well, like 0 to percent. We didn't want that, didn't want that, didn't want that. That is what I wanted. I think you do it like that. If you have it like the other way around, then it's like Intel, and then that's AT&T. Can't actually recall which was which, but there are two types, and I prefer this type where you have the destination as the first parameter, and then the second parameter is your, well, the second and further, if any, will be your like source parameters. So here we're basically clearing AX, we're moving 0 into AX, and then we're doing DS. We didn't actually do DS, but we can now. You can also have DS, which is data segment, and CS, which is code segment. And they're used for they're used for things. That didn't do it. There. It's weird that when you go down, it doesn't go down to the one that you did. Because like in Tmux, if you did the same, actually, yeah. So like in Tmux, if you go up, then you go down, it will go back to the same one you were in. But oh, didn't want to do that. What I might actually want to do is I realize that my webcam is like somewhere around here. I don't actually have anything hiding it, but what I could do is not sure the hotkey off the top of my head. That kind of works. Just doing that. What I might actually do is just kill this because I don't need that anymore. Yeah, so here we can kind of see things a bit clearer, hopefully. And I think the font's kind of reasonable. When I had a quick look, it looked kind of reasonable. But if the font's small, then let me know, and I can make sure that the font is at a certain size every time that I do one of these videos. So we basically clear AX, then we move that cleared value into the data segment. You can't actually move 0 into data segment, I think, from memory. This is kind of annoying. And then we moved the stack pointer to where it was, and the stack moves downwards, as we said. And then we moved the base pointer to where the stack pointer is. So the base pointer is kind of where the latest frame is. And when they are the same, they're at the bottom of your stack. That's kind of what it is. And then we push the base pointer. So we've started a frame. Here we do some stuff. So here we have that DL. So DL will be part of DX. And we're going to move it to a variable disk. And where is disk? Disk is here. It's basically a 1 byte allocation, basically, that is after some halt things. So this is basically in a place that it shouldn't be getting to normally, because it's basically right before the boot sector, because normally you would jump over all that into the second sector. It's just the way I laid that out. And so we basically move the, I don't know, we move the DL, the low byte of DX, which we never actually initialized. So it could be just like randomness. Oh, yes, that's right. The BIOS will actually set DL for us. So the BIOS will set DL to be uh, the index of which disk you are at. So if you're in partition one, there will be one. Well, if you're at partition one, it will probably be zero. If you're partition two, it will be so on, so on. So this will be basically the partition number of the disk that you're on. And so we basically store that somewhere because we want to do some stuff with it. Now, this enable A20 is like a trick that you do to have a bigger have more space to get with, because currently we've only got 512 bytes, and the A20 is like part of a chip on the um, CPU, well, part of a chip inside of the CPU that it deals with audio, I think, from memory. But if it's if it's set higher, then it does some stuff, and yeah, we do that, and that will return us the value in AX. So we basically test AX against AX, and what that will do is basically see whether it's zero or not zero. And if it's zero, we will panic. So this JZ is not the famous rapper. It is actually jump if zero. And there are like a bunch of other jump commands. So test is like testing against a bitmap. So like say if we tested 0x AB with 0x, I don't know, FF, that would return AB. If we tested it with 0, it would return 0. If we tested it with A0, then it would just have A0. And if we tested it with, say, 8, 0, it would have 8, 0, because A actually has that bit set. So you have 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. So if you have 1, 2, 3, 4, 5, 6, 7, this bit's set, that's 8, 0, and then A is like that, I think, maybe. I don't know. I can't really do conversion to binaries on the top of my head. But anyway, that test didn't think I did something that wanted to diff. That test will basically test against a bitmap. Test against bitmap. And you might see commonly using the source and destination as the same thing. And basically, if it's 0, then it will be 0, and if it's not 0, it will just be itself. And it's a cheap way to cheap as in bytes, to see whether it's 0. And yeah, then you have the JZ jump if 0. You also have JNZ jump if not 0. You have like a bunch of other things like JC, JB, JL, JGE, JLE, JE, except JE is actually the same as that, and J not equal. And these all test bits of a flag. So there's also like a flags register, which flags reg will have stuff like whether the last operation returned a zero or not. Zero flag. It will also have like a C, which is carry flag. So if the last operation resulted in carry, so if you do like 1+1, then it's going to be 1 0 with a carry of 1. So, well, the 1+1 is 0 with a carry of 1. So you can see when you've got a carry flag. So jump if carry, and these are already the same, so maybe it's GG. Not really the same. Jump if less ratio and equal and less or equal. That's not an and, that's an or. Right, and the JB is make my own thing. I'll come back to JB if we come to it, because seeing it in context might actually do. So here we do some stuff. So the BIOS has like a bunch of interrupts, like a lot of interrupts. The interrupts are your way of calling to the BIOS and saying, hey, I want this information, or hey, I want you to do this thing. You can't actually call into it like a jump or a call function. You have to do this interrupt. How you do the interrupt is you have interrupt of a certain number, which the BIOS will then be like, oh, that means it's a video thing, and then it'll look at AL and it'll be like, you want to set it into VGA text mode, and then, well, it'll look at AH, I guess, and be like, you want to set the mode of the video, and AL will say that it's text mode. And for some reason it's not actually set, but that will clear the screen. And here we call another function which I've written, which will read the disk. So it will basically read the entire disk into memory. Now, there's limitations to that because there's only so much memory that you can actually get at this point in time. So this will probably need refactoring at some point to not read the entire disk. It might actually just read the next sector. What we could do is have a look. We can look at source boost and some source like it might be in this BIOS. Yeah, so this is like where we have all these functions. So that enabled a 20 thing. All it does is basically hides some stuff. We see if we support the A20 line, then we check it what it is. Then if it's already one, then we just go yeah sure. Otherwise, we enable it and then we return. And we either return with AL being a 1 or a 0, or like AX being a 1 or a 0, and the function before will deal with that. So that we saw before called a function, and ret is return from function. And JB must be jump below. Yeah, I don't know. Like there's lots of kind of lots of things that are kind of all the same. But yeah, so here the bias does read, and I even say we shouldn't read past the 7FFF. So you may recall that we started loading at 7Z00, so loading up to 7FFF would be reading like a bunch more. It would be basically reading 0x7000 bytes more plus some to make up the FFF. Um, go down there, and I have a link to say like what happens. Um, so basically, you don't want to do that, but this would do it, and it would caused some errors. And as I was developing the operating system, I kept on running into these limits, and like weird stuff would happen. So now I actually have these like um, magic values, so I know when things are going wrong. Like I can check in the main kernel code, is the magic value what you expect it, and if it is not, then like nah, panic, something's gone wrong. But yeah, here we do a bunch of stuff. So it basically does some things. Oh, SBB, I think that's shift byte something. I don't know. There's like a bunch of things in that big fat book. There's also like online resources that you can see what each of these things are. So like if I don't know, I did something that I didn't want to do. Ooh, what do I want to do? I want to nah. Yeah, that's what I wanted to do. Yeah, so you can search in here. We'll have a look at things. This will probably explain it better than I will. So SBB into the subtraction with follow, and we can also look up that JEB that I didn't know what it was. And yes, I did mean this. So here, like JCC is like here are all the things. So JB is jump short if below. So yeah, so that's similar to jump if less than, but it's only a short jump. Whereas if we look for a JL, then it's a near jump. There's like different types of jumps, and yeah, there's different types of jumps. But yeah, anyway, so we what was that first one? This isn't the one I need. Integer subtraction with borrow, so that will like um borrow that zero and then yeah, so you can see what this does by looking up that it is a thing with uh a register or memory 8 and an immediate 8, and then it will subtract with borrow the immediate from the register. Um, and if it's AL, then it does it in particular. But that one has a shorter opcode because this needs uh, extra things. So basically, this is shows you how it can assemble everything. So you can try and like fine tune your bytes better. So like potentially, I could do this better if I had that in AX or AL. Sorry. But I don't know. There's lots of things that you can do. Actually, no, I was wrong. It was no, it is AX is a 16-bit. Yeah, so it would be this one, but it still does the same thing. Um, And div is a funny one. It divides and it'll put AL being the quotient, so the result of the division, and AH will be the remainder of the division. But yeah, so then we basically have the number of sectors that we need to read. We do some stuff, then we do like a bunch more stuff. So here we have jump less than, compare, conditional move if greater than. So here we only do the move operation it is if the last operation was greater than zero. We can see that the last operation was a compare, so we can see if basically if dx is greater than a, then we will move dx into there, like do a bunch of stuff. The semicolon is a comment in here in this dialect. And then we read some sectors, and then we do some stuff. We like pops and things. So that's like kind of all doing a bunch of stuff. But all it's doing is basically under the hood, it is reading the disk into memory. So here we get that disk that we saved before. So square brackets will mean that it will be a memory address of whatever's inside the square brackets, and that if it's a textual thing, then it'll just be a label that we've defined. And we saw us saving into that variable before. And then we do some stuff. EXC ECHG is exchange, so it will like basically flip the DLDH, and we'll do a bitwise and there's like a bunch of things. We'll do some like multiplication. Pop will like pull stuff off the stack, and the pushes and the pops will make funny noises in the microphone, but it will also increment and decrement the stack point. It'll basically go down if it's getting pushed, and it'll go back up if it's getting popped. And when it's equal to BP, then you're at the start of your frame. So you don't really want to do that, really. And XOR is bitwise XOR. It's all a bunch of stuff that like you would need to know, kind of low levels. SHL is shift to the left, so bitwise shift. You get all the bits and you shift them all to the left by 12 in this case. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then you're at the right place that you want. So this all does stuff, and as I said, it kind of just reads from the disk. We have a print function, so we can print stuff to the screen if we want to. And I have a thing that will print like characters, so you can see like we try and work out which character that we want to write. Yeah, so that's that. So maybe if we go back to this one. So we've read the disk, and then we jump to the second sector. Now this will still be a short jump, I think. So we can look at the jump. Yeah, so we got jump short, jump near, and jump far will be when we do something with a colon. So watch out for that. But in the second sector, we have basically loaded it here just after the magic value of the boot flag. So here was the MBR magic, the whatever it was, AA55, And here we have our second sector of the disk. So we're still in 16-bit mode. And here we do like the E820. E820. And I might actually like, while I've got a browser, A20 line x86. This will probably do a better description of it. Yeah, so it's basically one of the things. I think this one will be better. Yeah, so enabling the A20 will get us so we can have more than 1 MB of memory. So kind of good. Yeah, so if we enable the A20 line, all the memory can be accessed. It's just how it is. And the E820, E820, where are you? Yeah, here. Yeah, so all of x86s support the E820, which is just above somewhere. I don't know, sometimes you gotta like look for things. What? E80? Yeah, one of these is like the one that it's talking about. It doesn't seem to be there. But the gist is that E820 will get us our memory. And then we do CLI, which will clear CLI x86, clear lock interrupt, clear interrupt flag, yeah. The gist is that now we won't get any interrupts, which is very important because we don't want to have interrupts in this in between stage. You would get an interrupt for various things, like if someone typed on a keyboard, if like a network packet came in, if like the clock had a timer that just ticked over, like all kinds of things can cause interrupts. So here we clear it and then we load the GDT. The GDT is like global descriptor table, which that will global descriptor table. It's basically a certain structure that you have to have that will tell you all about the segments of memory. So we basically load it up to say this is where all the memory is based on what we got from the E820. Yeah, so that's all good. And then we do like a bunch of stuff. So we like have this CR0. Oh yeah, x86 registers. Now this one, osdev. I like the osdev wiki. So here you have like kind of what I described before, and then these two. It wasn't PC, it was IP, but that's the instruction pointer. And then you have the segment registers. So what we want to do here, we're getting the data segment, and we're basically setting the data segment, the extra segment, the general purpose F segment, the general purpose G segment, and the stack segment all to the data segment, which I believe is just 0 on my thing. And then we do a jump to the code segment colon protected mode. So that is going to do a long jump. Now that is important because when you do the long jump, you basically exit out of, well, actually, the CR0 is how we do it. CR0 is like we put this protected mode switch on, which is that first bit. We first get it, then we set the flag, then we put it back in, so we don't change any of the other bits, but we enable protector mode, and then when we do a long jump, it will basically you're in 32-bit mode there. So then protected mode will just fall through, and then that was I should just go buffer linker buffer link. Yeah, here. So we basically went from boot, and now we're going to load up whatever was in boot 32, and that is in boot 32. And here we set, we're using 32-bit mode, so we want to make sure that we're using 32-bit mode. And that's where it is. And so that is basically the process of going all the way from the 16-bit real mode where your computer starts up in all the way up into 32-bit mode. At this point here, you're not actually like in a very useful state, but you have like all the memory loaded, you have the disk loaded, you're in 32-bit mode, so you can do 32-bit instructions, you can do a bunch of things. I think the interrupts are actually still disabled, but maybe like one of these is no, we don't actually have that. But yeah, we're in 32-bit mode, and one of the big limitations is we can't actually get back into those BIOS instructions that were reading the disk and seeing where all the memory was. We can get back into that by going into like a protected real mode, I think it is. It's kind of weird, but I currently don't do that. Just because I don't know, there's no real point at the moment, but there will be kind of points because I'm only in text mode VGA, and if you want to change it, you might need to go back in and do that, or you can just talk directly to the VGA hardware and fiddle some bits there. But yeah, I think that is probably like a good overview of that. Helps me kind of get through some of the code rot, kind of understanding, yeah, this is how things did. I don't care about that buffer. And yeah, that's basically how you get from boot to a 32-bit environment that doesn't do too much. And maybe next time I'll keep on going and talk about what are the steps that I do in the 32-bit environment to then get a bit more of an operating system. And as I mentioned, I don't currently have the long mode, which is the 64-bit, so I won't be going into that in any of these videos, but I potentially will in future as more of a development stream where I'm actually developing it to show how you would go into long mode. And potentially also I would have another development video of showing how you would boot from UEFI, because I do have a new laptop that cannot run this operating system. It just can't. I thought just before we go, I could do like a, where we put it. So we actually have like an image that we have loaded, and this is kind of what it looks like at the moment, and it's got like a bunch of stuff. But if we had these git greps, git grep if we look at that for that AA55, we can also just like man, HXD, can we like limit? Uh, hold on. Um, yeah, minus L. Um, so maybe if we go minus L512, yeah, at the bottom here we can see this 55AA, and everything above that is just all the code that I just talked through. This is it, and you can see I don't actually have much room to spare. Like yeah, not much to spare. So each of these are 4 bytes. So 4, 8, 16, 32, and then that's another 32, 64, and then there'll be 126 bytes I have free if I wanted to add more to that kind of bootloader sequence. But there are like a bunch of redundancies I have in the code that I could clean up. And potentially I might come back to it because I'm not sure this is like the best way of doing it. And like one example of going over the limit was I used to have these error strings. They used to say error and error and error. So there's what? Uh, there's only two. 29. Yeah, there's only two, but they used to say error. And I saved 4 bytes by removing that, but I could add them back in, but I don't need that much. Thanks. That doesn't really matter. Yeah, it's kind of interesting. But yeah, that's the boot process of an x86 64 processor that I have in my operating system, and hopefully I'll see you next time. See ya.